Okay, so to finish this chapter, we're going to talk about expected value. An expected value can be thought of as a mean or an average. So if you want to, you could think of expected value as the average value. So we start this discussion by defining a random variable. A random variable is a function that will assign a number to each simple event in a sample space. Now you might remember from algebra that you could take a function defined by f of x equals 3x plus 2, and for every number that you plug in for x, it will assign a number to that. Like if you plug 1 in for x, it will actually give you an output of 5, so it will assign 5 to 1. If you plug 2 in for x, 3 times 2 is 8, so it would assign to the value 8. Excuse me. Well, for a random variable, we basically have the same thing, except the input values are not going to be numbers. They're going to actually be the simple events of the experiment. And the function or the random variable is actually generally going to be literally defined to represent something. So let's talk about an experiment here. Suppose a pair of 6-sided dice are rolled. Now we might be interested in the sum of the dice, so we're going to let S represent the set of the 36 possible outcomes. Now, since we're interested in the sum, we can assign the random variable X to represent the sum of the simple events. Now, I will only give you enough to list how this works, to show how this works. So let's say, suppose we roll a 1-1. Well, if you evaluate the random variable, and x is the random variable or the random function, if you evaluate the function at this simple event, since we know that x represents the sum, then the output would just be the sum of the two numbers in that simple event. And if you evaluate it at the roll 3-3, then we know that the output, when you input 3-3 into the random variable, the output's going to be 6. And then 4-3, the output's going to be the sum of 4-3, which is 7. For the simple event 6-3, the output's going to be 9, the sum of 6 and 3. Same thing for 3 and 6, the output's going to be the sum of the two numbers 9. For 5 and 6, it's going to be 11. For 6 and 6, it's going to be 12. So you can see that the input values are the possible rolls of the dice, but the output values are the possible sums, which range from 1 to 12. So you can see that the possible values of x are actually the numbers 1 through 12. Actually, it's not 1 through 12, is it? It's actually 2 through 12, because you can't get a sum of 1, right? So, my bad. So it's actually 2 through 12. Okay, let's look at another experiment. Suppose a pair of cards are selected from a standard 52 card deck. We might be interested in the number of aces we select. So if that's what we're interested in, then we're going to let the random variable represent that. Now, S is going to be the set of 52 choose 2 or 1,326 possible 2-card hands, which we won't need that for now, but let's talk about the random variable. The random variable X is going to represent the number of aces selected in a hand. Now you can see I listed a few simple events here. Obviously I'm not going to list them all because there's over 1,000 of them. But if you draw the 7 of hearts and the 8 of spades, then since X represents the number of aces, then actually X would be 0 for that hand because there's no aces. Same thing if you draw the 2 of hearts and the 10 of clubs, you're going to get 0 as well because there's no aces in that hand. Now, if you draw the ace of diamonds and the 4 of spades, or if you draw the jack of hearts and the ace of diamonds, then X is going to be 1 because there's one ace in each of those hands. Or if you draw the ace of hearts and the ace of clubs, or the ace of spades and the ace of clubs, then X would be 2 because there's actually 2 aces in that hand. So the input values are all of the possible 2-card selections, and the output values range from 0 to 2 because you can have anywhere from 0 aces up to 2 aces. So the values of X can equal 0, 1, or 2. Okay, here's another experiment. Suppose we answer 3 multiple choice questions that have 4 possible answers each, A, B, C, and D. Let's say S is the set of 64 possible answer sheets submitted. Now, let X be the random variable that represents the number of correct responses in a submitted answer sheet. Consider these sheets. Suppose 6 people turn in answer sheets. One person turns in AAB, the other one turns in AAA, and then one turns in BAC, one turns in BCB, one turns in CCA, the other one turns in BCA. Now suppose the key is BCA. Okay, so let's ask ourselves, since X is going to represent the number of correct responses, could a person get 0 correct responses? Well, of course they could. They could miss all 3. Could a person get 1? Yeah, they could get 1. Could they get 2? Yes. Could they get 3? Yes. But could they get 4? And the answer to that is no, because there's only 3 questions. So the most they could get would be up to 0, 1, 2, or 3 correct answers. Okay? So the random variable can actually equal 0 through 3 correct answers. Okay, and again, I'm not going to give you each simple event. Okay, I had to make some corrections on my sheet here. This is kind of complicated to set up. But let's say a person turns in these values. Okay, so what I meant to have here was these 6 answers. I'm not sure how I got what I had. But anyway, so if a person turns in the sheet AAB and X represents the number of correct answers, well, remember the key is BCA. So if they answer AAB, then they're going to get none of the answers correct. So X is going to be 0. Now if they turn in the sheet AAA, well, they're going to get only the last one correct. So in that case, the random variable would equal 1 for 1 correct answer. If they turn in BAC, then let's see, they would only get the first one correct. So that would be 1 correct answer. If they turn in BCB, then they get the first 2 correct. So that means X would equal 2 for 2 correct answers. If they turn in CCA, then they get the last 2 correct. So again, X would be 2. And if they turn in BCA, they get all 3 correct. So for each of these simple events that are turned in, then you can get anywhere from 0 to 3 for the X value. Okay, let's go back to that problem I just did. And let's remember that the key is BCA. So remember also that the X values, they could get none correct, 1 correct, 2 correct, or 3 correct. Let's take a look at how many ways this could happen. Now, you know that, or each of these could happen. Now, you know that there's 64 possible answer sheets that could be turned in. Well, to get 0 correct, then they would have to miss all 3. So that means, since there's only 1 correct answer, that means they would have to choose the 3 incorrect answers for the first one, the 3 incorrect answers for the second one, and the 3 incorrect answers for the third one. So that would be 27 ways to get 0 correct. Now, this one gets a little tricky. So if X equals 1, think about it like this. To get 1 correct, you have to either answer number 1 correct and get 2 and 3 wrong, or you have to answer number 2 correct and get 1 and 3 wrong, or you have to answer number 3 correct and get 1 and 2 wrong. Well, let's assume you get number 1 correct. Then that means you miss 2 and 3. So that means there's 3 choices for 2 and 3. There's only 1 choice for number 1, the correct answer, and for 2 and 3 there's 3 choices in order to get the first one correct and the second 2 wrong. So if you multiply 1 times 3, that's 9. Well, you're going to have the same number of ways to get number 2 correct, and you're going to have the same number of ways to get number 3 correct. So if you add those together, 9 plus 9 plus 9, you're going to get 27 possibilities. Now, let's talk about the ways you could get 2 correct. Well, you could get number 1 and 2 correct and then miss number 3. But remember, there's only 3 ways to miss number 3. Or you could get 1 and 3 correct and miss number 2, but there's only 3 ways to miss number 2. And then you could get 2 and 3 correct and miss number 1, and there's only 3 ways to miss number 1. So that means that there's 3 ways to do this, there's 3 ways to do this, and there's 3 ways to do that. So there's 9 ways that you can get only 2 correct. And then finally, there's only 1 way to get all 3 correct. So now, what's interesting is if you add these numbers, 27 plus 27 plus 9 plus 1, it adds up to the 64 possibilities. Now, something else I can do from this is, since I know the number of ways to get none, 1, 2, or 3 correct, I can actually determine the probability of getting none, 1, 2, or 3 correct. So the probability of getting none correct, well, since there's 27 ways out of 64 to do that, that probability is 27 out of 64. The number of ways to get 1 correct would also be 27 out of 64. The number of ways to get 2 correct, well, there's 9 ways that can happen, so that would be 9 out of 64 for the probability. And the number of ways to get 3 correct, there's only 1 way out of 64 to do that. Now notice, if you add these 4 probabilities together, which of course exhausts all the possibilities, then that's going to add up to 1. So there's a 100% chance that you're going to either get 0, 1, or 2, or 3 correct if you turn in an answer sheet. Now this table up here is actually called the probability distribution for the random variable. So the properties of a probability distribution of a random variable is basically kind of mirrors what we talked about for acceptable probabilities. The probability of each event for each of these events has to be between 0 and 1 inclusive. They can be 0, 1, or any number in between. And you'll notice each of these numbers are some value between 0 and 1. And then the other thing is that the sum of each of those probabilities must add up to 1. Okay, and like I showed you there, all of these add up to 1. So now let's go back to another experiment and let's see if we can come up with the probability distribution table. So we toss 3 coins and we're interested in how many land heads. Well, we know that you can get no heads, 1 head, 2 heads, or 3 heads. So we're going to let X be those values. Now I went ahead and listed all of them. There's only 8 possibilities here. And so there's 1 way to get no heads. There's 1, 2, 3 ways to get 1 head. And then there's 1, 2, 3 ways to get 2 heads. And there's 1 way to get 3 heads. So if you do the probability distribution for these values 0 to 3, then the probability of getting no heads would be this 1 way out of 8. So the probability would be 1/8. Now if you want to know the probability of getting 1 head, well, it would be these 3 values right here, or 3 ways right here out of 8. So there's 3 ways out of 8 to get 1 head. And then there's also 3 ways out of 8 to get 2 heads. So the probability of getting 2 heads would be 3/8. And the probability of getting all 3 heads, there's 1 way that can happen out of 8. So that would be 1/8. So that's the probability distribution for that random variable. We finally get to the area of where we can calculate the expected value of a random variable. Basically, once you have the probability distribution, x1 and its corresponding probability, x2 and its corresponding probability, and so forth, then you can get the expected value of the random variable by just summing the products of each x value with its probability. So go back to our experiment that I just did. Here's the probability distribution table for tossing the 3 coins. And notice if you take 0 times 1/8 plus 1 times 3/8 plus 2 times 3/8 plus 3 times 1/8 and you add all of those up, you're actually going to get 12 over 8 or 1.5. Now let me finish this video by telling you what this means. It means that if we toss these coins over and over and over, we should average 1 point head per trial. Another way to look at it is if you did this experiment 100 times and tallied up the number of heads you saw, let's say you counted 130 heads, then the average number of heads per trial would be out of 100 trials you got 130 heads, so you averaged 1.3. So it's slightly, I said higher, but it's actually slightly lower than expected. You're expected to get 1.5, so it's slightly lower. Now if you did the same experiment on 3 other coins and got 420 heads, that would be an average of 4.2 heads per trial. Now you might question if the coins were actually fair coins. And we'll do some more examples of expected value on the next video.